Hey, what's up guys? It's Nick the Quant. This is my first time posting a video going over the highest edge out of all the model plays that I run. You can get access to all of my plays every day for free on my X account. I post every single pick there, the low edge, high edge, whatever it is, and I immediately post them once I'm done running the model. So in order for you to be up to date the most, immediately being able to act on these picks, you can follow my X account and turn my post notifications on. With that being said, I want to make it a daily practice every day to give a video analysis on the pick out of the entire slate that has the highest amount of edge. That way I can show you guys exactly what goes in to the model and how I find edge in these plays. This routine, how my model runs, is the same. It's a system on every single play, but being able to illustrate how you come to a conclusion on having the highest amount of edge is something I really want to do to show you guys full transparency. So with that being said, my model, it's an ensemble model. It's got 9 interior models. I've posted a lot about this in my X account, kind of breaking down exactly what goes into it. So first what I'm gonna do is there's gonna be 3 stages to this. I'm gonna break this down just like how my model would. I'm gonna talk to you guys about what the interior models had. All the interior models are calibrated. And then I'm gonna get into the second stage of calibration and the third and final stage of calibration, which is where the pick is, or the prediction is finalized. And that's where we can assess if we have edge or not. Okay, so I'm gonna kind of try to illustrate this on the screen the best I can, but the first model in my ensemble model that I ran had the Angels initially at a 62% probability. But like I said, all of the models, both the interior and the ensemble output, and the third stage of calibration as well, they're all calibrated, meaning you can't just blindly trust a model's output because you don't know what its correlation with the real world results are. Meaning, if a model produces, say, a 55% probability, in theory, a 55% probability along its distribution means in 55% of potential outcomes, that probability should take place. But the problem is when you blindly trust a model, you don't actually know what the true probability of said prediction is. A model can say an event has a 55% probability, but across 100, 200, 1,000, whatever, predictions, you might see that it's performing at a higher rate and it's actually accurate 60% of the time, or it could be performing and underperforming and it's only accurate 45% of the time. So actually being able to see what the honest prediction of that probability is based on the empirical data that you have, that's how you can actually understand what the true probability is when your model says whatever this is. So getting into that, I just kind of wanted to explain that before getting into this. So model 1 initially had the Angels at a 62% probability. Up to this point in the season, that's been an overperforming range. So model 1 finalized the Angels at a 58.96% probability. Model 2 initially had the Mets at a 50.4% probability. That's been overperforming very largely throughout the season. So it finalized the Angels, Model 2 did, the Angels at having a 57.89% probability. Model 3 had the Angels at a 54.6% probability. That's been an underconfident range, meaning that the outcomes have been exceeding a 54% probability. So this is a good performing range right here for Model 3. So Model 3 finalized the Angels at a 59.58% probability. Model 4 had the Mets at a 54.27% probability. That's been honestly a really accurate probability throughout the season. Calibration slightly raised the Mets on Model 4 to the Mets being a 54.85% probability. Model 5 had the Mets at a 65.24% probability. This has been an overconfident range, so calibration pulled that down, finalizing Model 5 probability for the Mets at a 61.47% probability. Model 6 had the Angels initially at a 65.16% probability. This has been a little overconfident, but not too much. Calibration slightly pulling this down. Model 6 finalizes the Angels at a 64.57% probability. Model 7 initially had the Mets at a 61% probability. This has been underconfident just a little bit, meaning it's been performing at a good range. So probability slightly pulls it up for the Mets on Model 7, finalizing the Mets at a 62.9% probability for Model 7. Model 8 initially had the Angels at a 55.19% probability. Again, this has been a little bit of an underconfident range, meaning it's been performing higher than what you would expect given the model's initial probabilistic projection. So that pulls it up. So Model 8 had the Angels at a 58.72% probability. And now lastly for Model 9, initially having the Mets at a 52.44% probability. This has been a really accurate probability range, just a little like slight decimal points off. So calibration for Model 9 confirmed the Mets at a 52.14% probability. Okay, so now getting into the second and third layer of calibration. So our interior models are all calibrated. That runs through, and the weights of the models are determined by their Breyer scores, meaning how accurate their probabilities are. A Breyer score is a way to measure how well a model is doing with the probabilistic projections it's making. A good example is if you have a model that produces, let's just say 5 predictions, 3 of them are somewhere in the 50s, 1 of them is in the mid 60s, and 1 of them is somewhere in the 70s. You could go 4 and 1, meaning the 50s hit and the 60 hits, but that high 70 projection misses. Your Breyer score is going to tank because, again, probabilities function on a distribution. So in that sequence, the most likely one of those predictions that should be successful should definitely be the one that has a higher probability, up in this, like let's just say it's 78% probability. So if you have a model that is consistently missing at these higher probability projections, clearly these probabilities are not accurate, so the Breyer score will reflect that, and that's why calibration is so important. So I'm going to get in now to how I calibrate the ensemble model's output. I'm going to get into it initially outputted based on everything I just broke down across those 9 interior models, the second layer of calibration, and then the third layer. Okay, so the ensemble model initially, after all those 9 models ran, according to their weights, etc., had the Angels a slight lean at 50.8% probability. Now, on the season, when my ensemble model produces a prediction that is anywhere below 51% but above 50%, so anything from as small as 50.01 up to 50.99, this currently has only been 46% accurate on the season, meaning it's overperforming or overconfident in this range. So second layer calibration, just like the interior models, takes that into account and calibrates that output. So it brought down the Angels to a 49.22% probability at the second layer of calibration. Now the third layer of calibration is something different. This is something where I run my model and I track market dynamics, or market regions is what I like to call them. So I track the amount of money that are on baseball teams that where the favorite in the matchup cannot be any larger than minus 200. So there has to be a specific range of money line that is tolerable for my money or for my model to be ran on it. I track this, and right now there's a clear trend. There's 2 regions of money. They looks like sharp money that has been performing very well on the MLB. One has a 63% overall hit rate, and the other has a 71.7% hit rate. And they have good sample sizes, both almost in like 100 plus games. So the Angels today align with that hot region, which is a 71.7% hit rate. So definitely some sharp alignment on the Angels right now. So that second layer of probability, the Angels at the 49.22, gets calibrated by the third layer being where their market dynamic alignment is. Taking that into account, now the final probability for the Angels is a 56.84% probability at +1. A little over, the books are deferring. DraftKings kind of has them oscillating between like a 103 to a 108. But most books close anywhere from like +100 to +110 odds. So the odds I got it at exhibited the Angels being at +15.95% positive expected value. I use Kelly Criterion. Again, everything I try to do with my model, I base solely on the rules of probability theory. So the risk I'm taking is all based on the probabilistic edge. So given that the expected value in this matchup, I take right now a 1/6 of a Kelly, because Kelly Criterion is definitely a very aggressive way to essentially risk money, whether it's in sports betting or it's in options, because Kelly Criterion assumes your probabilities are 100% accurate, which in sports is almost impossible, or really anything if you're predicting something that is quite volatile, has a lot of variance in it. So that's why it's important to really scale your Kellys. So right now I take a 1/6 of a Kelly, meaning because of that, I'll be risking 2.55% of my bankroll on the Angels today, which is 2.55 units, 1 unit for me is 1% of my bankroll. So to conclude, this high edge play is the LA Angels on the money line. I'm risking 2.55%. They got a 56.84% probability, and this is today's highest edge play. If you want to see the rest of my plays, again, if you want to see them immediately, you can check out my X account. There I post all of the plays right as my model runs through them. I denote the expected value, I denote the money line I got them at, and I denote the risk that I'm putting on them. But again, like I said, I want to do a daily analysis video on the highest edge play I find on the slate. Thanks for watching, leave a follow, and let's get this bread.